Case studies. Here, in a few examples, our income on the field of swarm intelligence principles in computer games and gamesourcing is mentioned. Some of them were already published in conference and journals, so for more details, it is recommended to follow the references in the text. First of all, we will discuss the use of swarm algorithm Soma in Tic-Tac-Toe game, which is released on Google Play Store, and anyone can easily download and play this game. Swarm intelligence is a counter-player against human one in this game. The second one is utilizing Soma algorithm in the famous game StarCraft, Brood War. Swarm intelligence was controlling a combat unit strategy of movement in extraterrestrials wars, as explained in. The real Gamesourcing is in the next section, where a human crowd plays a game labyrinth, that is equivalent to a traveling salesman problem, TSB, problem. The results are then compared with ACO algorithm applied on the same problem. At the end is introduced our new platform for Gamesourcing Labyrinth 3D for more extensive experiments. This application is focused on swarm intelligence techniques and their practical use in a computer game. The aim is to show how a game player, based on swarm algorithms, in this case, Soma, can replace a man in computer games. This provides an opportunity for effective, coordinated movement in the game fitness landscape. The implementation of our experiments uses classic techniques of artificial intelligence environments, as well as unconventional techniques, such as swarm intelligence. Research reported here has shown the potential benefit of evolutionary computation in the field of strategy games. Soma is a stochastic optimization algorithm that is modeled based on the social behavior of competitive cooperating individuals. It was chosen because it has been proved that this algorithm can converge usually toward the global optimum of the given problem. Soma works on a population that consists of the possible candidate solutions in iterations. They are called migration loops. The population is initialized, as usual for this kind of algorithms, by uniform random distribution, i.e., over the search space at the beginning of the evolutionary search process. In each migration loop, the population is evaluated, and the individual with the lowest cost value, the best fitness, becomes the leader. Apart from the leader, in one migration loop, all individuals will traverse the space of possible solutions in the direction of the leader. Mutation, the random perturbation of individuals, is an important operation for Soma. It ensures diversity among all the individuals, and it also provides a means to restore lost information in a population. The mutation process is different in Soma as compared with other evolutionary algorithms. A parameter, called Prt, is used to achieve mutations and perturbations. This parameter has in Soma the same effect as mutation for other EAs. The Prt vector defines the final movement of an active individual in the search space. It is a randomly generated binary perturbation vector, which controls the allowed dimensions for an active individual. If an element of the perturbation vector is set to 0, then the individual is not allowed to change its position in the corresponding dimension. An individual will travel over a certain distance, path length, toward the leader in finite steps on path length. If the path length is chosen to be greater than 1, then the individual overshoot the leader. This path is perturbed randomly. The main principle of Soma, i.e., traveling of an individual over space of possible solutions, is depicted in. The initial parameter sets of Soma for our experiments can be set in the Android program, as demonstrated in figures 2 and 3. For more details about Soma, see. Soma can be considered as a member of swarm intelligence class algorithms. The Soma principle. Soma setting in Tic-Tac-Toe. Soma setting in Tic-Tac-Toe, strategy setting. It is true that all experiments are influenced by the player itself and algorithm setting. The screenshot from one game is depicted in figures 4 and 5. If Soma parameters would be set differently in a non-optimal way, then, of course, the performance would be different. Thus, the performance of the Soma depends on two factors, human skills and Soma setting. For more details and game description, it is recommended to refer in game on Google Play Store. Tic-Tac-Toe screenshot. The game in the process, blue cross, human player, green circles, Soma. Game over. StarCraft, Brood War is a well-known real-time strategy game in which swarm intelligence was used again. Soma implementation is focused on applications and practical utilization in combat units control. The goal of the war, and its results are partially reported here, is to implement computer player replacing a human in a real-time strategy StarCraft, Brood War. The computer player behavior is provided by the decision-making tree together with Soma and is used to remote movement of combat units. A particular implementation of Soma algorithm provides an opportunity for efficient, coordinated movement of combat units over the map. The work and its results reported in has shown great benefit of evolutionary techniques in the field of real-time strategy games. Similar to other strategic games, it is also crucial to provide acceptable amount of resource materials for creating an army to win. Materials are located on several places as well as at the starting position. The game allows a choice of 3 races, the Protoss strong extraterrestrial beings with inexpensive units. The Zerg seems to be primitive and overgrown kind of insects. Their units have a low price and are weaker than Protoss units. The last race is Terrans, a race of human-like being, a compromise between mentioned races that have balanced prices and efficiency of their combat units. For the use of the Soma swarm intelligence, a Zerg's race has been chosen. The techniques such as decision-making tree or unconventional techniques in the form of evolutionary algorithms, Soma algorithm, have been used. The algorithm controlled a movement of the combat units on the landscape. The game also further do not allow random placement of a population on the landscape. Starting positions of the units are on purpose near the structures used for production of the units. In the case of the incorrect objective function, we would be challenging problems with the speed of finding the enemy. The contact with the enemy would stabilize the process of searching so that searching units would be attracted to this place. It can be solved by the right setting of the parameters of Soma algorithm and modified implementation of the objective function. Other problems could not be solved this way. Parameter path length was set to a value 1 for the units to stay on the position of the leader. Experiments have shown that various numerical settings of the parameter step were not so beneficial, and small numerical values had no significant impact on the combat unit performance. The unit was particularly searching by step long as its own, it was set to step equals 0.5. Parameter Prt was selected near 1 so that the units would not deviate from each other so much, and at least some random searching came to pass. Prt was set to value 0.8. Dimension was set to 2 since we were searching in two-dimensional map given by coordinates and y. Pop size is an adjustable parameter. Each combat unit was added to the population until its death. All the Soma stop criterion, i.e., migrations and min-div were ignored. Soma was working through whole game until any unit was present. The positions of the enemy units were a part of the fitness function as well as important locations on the map. Soma algorithm thus works on the dynamic function in order to maximize success of combat units to win. The largest value was associated with the enemy units. The biggest fitness, the more enemies are present there. The closer position of the individual to enemy position guarantee the bigger fitness. Starting position itself was set to 0. The significant problem in this implementation was a non-random placement of the population as well as the inefficiency of the random search on the landscape. The position of the headquarters of the enemy was known. It is one of the starting positions. These problems were solved by the division of the population into 2 subpopulations, static and dynamic. A dynamic subpopulation consists of a classical individual who yields to recombination and mutation. It is migrating individual in the terminology of Soma algorithm. Static individuals, on the other hand, are not migrating. They are located in the important positions on the map-like locations with materials and starting positions. They can also be placed on the position of each existing structure. Their role is important because the static individual, at the starting position of the enemy, is calculated the biggest fitness. Moreover, they attract all of the units albeit from only one position. If they encounter the enemy on their route, this kind of individual is chosen as a leader, regarding the highest value of the enemy's hit points. If any of our structures are attacked by the enemy, this structure is activated to be a leader, there is a static individual. In this case, the leader will attract friendly combat units. These individuals also create a kind of alarm system.